Hi, thanks for joining me today. I've got another video, mock interview video, where this time I'm going to be on the receiving end of the question. So I've got Dev here, who, if you saw one of my recent uploads, I was asking him some questions. He's an economics graduate from the University of Cambridge, and today he's going to be asking me some interview questions and keeping me on my toes.
Yes, very excited to get started. So I prepared this in mind for any mathematical subjects, so economics, maths, computer science, or even natural sciences. So we'll get started.
Awesome,
Thank
cool.
you for, sorry.
Oh, no, sorry. I was just saying, yeah, that's cool. I'm excited to
Okay,
start.
cool. So we'll start with some calculus and some graph sketching type questions. My first one is, can you differentiate why it's equal to log x to the power of 1 over x?
Sure, awesome. So I presume you mean differentiate with respect to x, both sides
Yes,
of this equation.
yes,
Cool, awesome. So there's a few ways to kind of go about this. And the key thing that I'm noticing here is that we have an x in the power, which means that we probably it's probably going to involve a natural logarithm, even even if this wasn't ln of x, there's probably going to be some natural logarithm stuff in there. The best way of doing this, I think, is just taking natural logs on both sides and then proceeding by doing implicit differentiation. So if I take the natural log on both sides, I get ln of y equals 1 over x times ln of x here. And now if I just differentiate both sides implicitly with respect to x, on the left-hand side, ln of y would become 1 over y times dy
So
by
just
dx.
quickly, can you explain
Sure,
why that happens on the left-hand side?
sure, yeah. So maybe if I write on the side over here, can you still see my writing on the right-hand side? Was that too far right?
Yes, too
Okay,
far,
amazing.
or
That was
like
too far. Okay,
too far, a little bit.
let me maybe readjust it. How about here if I write
Yeah,
that?
yeah, yeah, I can see.
Okay, cool. Okay, so on the left-hand side, what am I exactly doing? Well, I'm trying to do the derivative of ln of y.
Yeah,
So the derivative with respect to x of ln of y. And the implicit differentiation is just a fancy way of saying a particular application of the chain rule.
yeah.
So all I'm going to do here is swap my x here for a y. So this is going to be equal to the derivative with respect to y of ln of y, almost. Of course, I can't quite just change the x to a y, but the chain rule says that, well, what I can do is take this and multiply this by dy by dx. And it's not exactly why, but informally we can think of those dy's as sort of cancelling out. It's a little bit more than that, but that's maybe just a useful way to remember it. But yeah, the derivative with respect to x of ln y is just the derivative with respect to y of ln y times dy dx. And this thing here is precisely 1 over y.
Yep.
It's 1 over
Good.
y and then times dy dx,
Yep. Sure.
which is what we have here.
Yep.
Awesome. Cool. Um, and so yeah, so we've differentiated the left side on, obviously that's got to equal the derivative of our right hand side. So just draw maybe a line here so I don't interact with the writing on the right. Okay, so we've got a weird expression here, 1 over x times ln of x. So probably going to have to use the product rule here. So the derivative of, we've got two functions, this guy and this guy. So I'm just going to differentiate one of them, keep the other the same, and then swap them around as you would with the product rule. So if I differentiate 1 over x first, I know that that's minus 1 over x squared, and then multiply by ln of x, like so, and add on to that, keep 1 over x the same, and then take the derivative of ln of x. And so to differentiate ln of x, I need to use the chain rule. So I want to make sure I don't make a mistake here. So this will be, um, if you want me, I think it's probably actually useful here, so I don't make a mistake. I'm going to call this thing here u.
Yep.
So the thing that I'm putting here is going to be the derivative with respect to x of ln of u. And now again, I'm just going to use like the chain rule. So this is going to be the derivative with respect to u of ln of u multiplied by du dx.
Yep.
This thing here is just 1 over u and u is ln x. I'm kind of jumping a few steps here because about to run out of space. So that'd be 1 over ln x. And then du dx is the derivative of ln of x, which would be just 1 over x,
Yep.
like so. So this is going to be, oh, hold on a minute. So I've differentiated ln of x. So that's going to be the 1 over u times
Yeah,
du dx.
so this thing would basically go here, right, in the bracket.
Correct. Yeah. Yeah. I was a little bit confused for a second there because I've got two ln's here and one here, but I forgot that u kind of has an ln embedded inside it. So yeah, this would be 1 over x. Uh, sorry, 1 over x, ln of x.
Cool.
Right. So, and then we could probably make a common denominator if we wanted to and put this together if you'd like me to.
Yes, please.
Awesome. So on the left side, we'll keep it the same. And the right hand side, I got a denominator of x squared here, a denominator of x squared ln x here. So let's just make a common denominator of x squared ln x. And then on the left, the first term here, we're going to multiply top and bottom by ln x. So it become, or I've got the minus ln x, ln of x,
Yep.
and then just plus 1. And then the last step here to get dy dx is multiply both sides by y to get rid of
Yep.
that term equals, um, so just I'll keep the terms the same.
Yes.
And then I'm multiplying this by y, which was right at the start, ln of x to the 1 over x. So I can maybe put this in brackets here and put ln of x to the power of 1 over x, like so.
Very nice.
And awesome.
That correct. Now, the next part of the question is if I give you an axis of x and y,
Mhm.
can you just think without doing too much maths, just intuitively how the graph of log x to the 1 over x will be shaped? So
Um,
just verbally, what do you think like are some characteristics of this curve?
okay, cool. So just to confirm, it's the function that I just differentiated. We want to think about what the graph of that would look like.
Yes, so the graph of log x to 1 over x power.
Okay. So my first thoughts generally, whenever sketching a graph, which is a bit non-standard, that isn't like a one of the ones that I kind of just know, is maybe just first to get an idea of it, maybe think about the intercept. So what I would firstly do is maybe plug in what happens when x is 0, but I immediately realize that's going to cause a bunch of errors because I can't do ln of 0. And even if I could, I've got 1 over x in my power, and I can't do 1 over 0. So I may have to think about limits as x approaches 0 here. I presume this graph is only defined on the positive parts, like for x bigger than 0, so on
Yep,
this section.
yep.
And when x is less than 0, there won't, or less than or equal to 0, there won't be anything. So I think
Do you
about the
think
intercept.
do you think is defined between 0 and 1?
Do I think it's defined between 0 and 1? Um, so ln of x is well defined, but it would be negative, and 1 over x will be a large number in inverted commas. And so do a negative number to a large number. So that won't exist in general because 1 over x, if x is between 0 and 1, the graph probably won't, well, unless x is of the form 1 over a positive integer. So let's just say, for example, x is 0.35, just for illustration, then x is not in the form 1 over n. And so when I do 1 over x, I'm going to get a positive integer plus a decimal, a small decimal. And the issue is I can't do a negative number to the power of a decimal number without entering into like the complex world. So the graph won't have it won't have a value on between 0 and 1. Technically, there'll be lots of little dots here for all the values where x is of the form 1 over n, because you can do a negative number to an integer power, but in general, there won't really be anything between 0 and 1.
Yep.
So I actually hadn't thought of that, but yes, that's something that we'd have to worry about
Cool.
if ln of x is negative. However, if now that begs the question that if x is at least 1, will the graph exist? And I believe it will, because if x is at least 1, ln of x will be positive, and then a positive number you can raise to any kind of real number power, and there won't be any issues.
Okay.
Um, so maybe I'll start my graph from one, and yeah, so it would start from the x into it would have an x it would cross the x-axis at one because ln of one is zero, zero to the one is still zero. So to start at one, um, as x gets bigger, my without I could do some maybe apply L'Hopital's rule, for example, or maybe just do some experimentation with large values of x. But intuitively, I'm guessing that as x goes to infinity, ln of x is going to go to infinity, but 1 over x, it's in the power. I feel that gets to zero much more quickly than ln of x does. And so I believe that ln of x to the 1 over x would approach zero as x tends to infinity. And so
Zero,
my graph is, oh, sorry.
0 or 1.
Um, oh, sorry, one. Sorry, yeah, sorry, one. Because it'll be 1 over x will approach zero. So ln of x, it'll be something to the power of zero, or something approaching zero, and so it would approach one. So if I have one here, and it's going to come from above, so I believe it's going to kind of
Why
have
is
an
it coming
asymptote.
from above?
Because for x bigger than e, so e is maybe approximately here. If I use one as a scale here, if x is bigger than e, ln of x is going to be bigger than one. And so it the so if I may pop this on the side here, ln of x to the one over x. If x is bigger than e, this is going to be bigger than e to the one over x power, and e to the one over x is this thing here is guaranteed to be bigger than one because e is bigger than one, and one over x is positive. So this is going to be like bigger than e to the zero, which equals one, for
Yes.
example. So all the y values will
Also,
be bigger than.
yeah, also intuitively we can think of it like 1 over x is always weakly positive, even though it gets close to zero. So I have a very large number raised to a power that is just slightly above zero, just slightly above 1, not exactly 1.
Yes, yes, I agree. Although I would still want to just double check. I know LNX grows very slowly, so I'm pretty confident that this will be quite slow, but I'd probably try and use something like L'Hopital's rule to verify that it does indeed approach one and not some other constant or even infinity. But I believe ln of x is one of those very slow growing functions, certainly in comparison to 1 over x, even though 1 over x grows quite slowly. Um, and it would obviously have to have some sort of turning point because we know it's when x equals e, ln of x is one, so it's going to be one to the power of one over e, so it's going to pass through this point here. I'm going to guess it's going to look something like this, and then it would have to have some turning point somewhere over here, which we could potentially work out with calculus using what we did earlier and setting that derivative to zero. I believe it would only have one turning point, more just from I can't really see why it would have more than one turning point. But I guess it potentially could have more than one turning point. But if I was to hazard a guess right now, without doing any further calculation, I'd presume it has this kind of sort of shape. But I'd have to, I'm not sure if this is perfectly to scale. Like, I'm not sure if this is, like, according to my y-axis, this maximum looks like it's about three. Maybe it is, maybe it isn't. I'm not too sure.
No, I think it's fine. Like, it's good. Let's consider a different sort of question, which
Sure.
applies different techniques to logarithms. So now I'm going to give you two functions. First, it's y is log x, and the second function is that y squared is equal to x minus 1 over x squared. The question is if I equate these two functions together, um, how many real number intersections, like basically how many real roots would they have?
Okay. So are you saying if I was maybe to sketch the graphs of both of these on top of one another on the same set of axes, how many times would they intersect?
Yes, that could be one way to think about it.
Okay. Um, cool. Okay, so my first thought is maybe to actually just try and sketch both of these
Okay.
and to physically count the number of intersections. I know I can sketch ln of x and get the rough shape of that. The second graph is a bit more awkward. Um, I also noticed that the second one is y squared, so it may have for any x value, it may have two potential y values. So just to illustrate what I mean by that, like with this one, if I was trying to sketch it and I was trying to work out what y was when x is 3, let's say, I'd get 2 over 9. And so the two possible y values that it could be is root 2 over 9 and minus root 2 over 9. So it's going to be kind of symmetric on about the x-axis when I sketch this graph here. Um, so that's just an observation. I'm not sure whether that's useful or not. So that's one way of doing it. I get to potentially approach this problem is just by trying to sketch both of these. The other way is maybe a bit more of a brute force method of just kind of maybe squaring both sides here and substitute or make it and setting this equal to this and trying to solve that. Although I don't think that's going to be particularly pleasant for two reasons. Firstly, I'll have an equation with both algebraic terms, so like x and x squared, and also logarithmic terms, and they're kind of difficult to it'll be difficult to solve that equation. Actually, well, sorry, 1 minute, 1 minute. Could you remind me of the question? Sorry, was it to work out the solutions or how many solutions there were?
How many?
How
So the
many? Okay,
number.
so that's an important question to clarify because if it's how many, then it is just a matter of noting how many solutions there are. So you don't necessarily need to work out what they are, just how many. So potentially there is a way to do this by squaring these and making them equal to each other. Um, um, okay, so maybe I'll go down my first route. So if I just get rid of the squares and actually try and sketch both of these, so I'll just get rid of this for the time being. So I'm going to start with ln of x. Um, and I don't need to worry about what happens when x is negative because there won't be any points of intersection there because ln of x won't exist. So I can start by sketching ln of x, which looks something along those lines. So that would be the first guy. Cool. Now the second graph, y squared equals x minus 1 over x squared. Um, Again, my first thought is maybe let's think about intercepts. So when x is well, actually, one thing I've observed straight away is well, when x is 0, this graph doesn't exist because we're dividing by 0. But in fact, we need x to be at least 1 because if x is less than 1, the issue here is that the numerator will be negative. The denominator is always non-negative, so it'll be this expression will equal a negative number, but y squared can't be a negative number without entering into the complex numbers. I presume here we're going to assume x is at least 1 in order to sketch this. Okay, cool. So first thought is, okay, well, then what happens when x is 1 then? Well, when x is 1, we get x minus 1 over x squared is 1 minus 1 over 1 squared, which is 0. So if I maybe use different colors here, I'll do this one in green. I know it's going to pass through this point, which is 1. So
Yeah.
it's going to have at least one intersection point straight away. Then I want to think maybe what happens when x is getting bigger than 1. Um, so a bit like the last problem, I can maybe think, okay, x squared here is probably, because the denominator here has a bigger degree than the numerator. I know when x tends towards positive infinity, this expression will approach 0. Um, so would you like me to illustrate why this approaches 0 when x approaches infinity?
I think the intuition is fine.
Okay, awesome. So I know that it's either it's gonna do both this and this. At the end, again, going back to that comment earlier about that this is going to be symmetric on the x-axis. So it's going to kind of approach from top and bottom. So I guess for the time being, it's sufficient to look at what happens above the x-axis. So let's say it turns out my graph looks like this, then I'll know that underneath the x-axis, it will look like this. And I've actually just realized it doesn't really matter what happens underneath the x-axis either, because clearly there's not going to be any points of intersection because the lnx graph doesn't enter this territory of like this area here. So there won't be any points of intersection there. But maybe for completeness, I'll still draw it on the bottom. But I'll focus on what happens above the x-axis. Okay. Um, the other thing maybe it might be worth considering is does this graph have a turning point? And so if it does, it definitely has to have at least one because we know it's going to go up from this point and it ends up coming down here. And because of things like continuity, there's got to be at least one point here where it turns around. Because if it didn't, this graph would, well, have to, there'd be no way for it to kind of join up here. It'd have to turn around at least once. I mean, maybe it turns around multiple times, but it's got to turn around at least once. Um, okay, so maybe the natural thing then is to find the derivative. It's not going to be pretty, but again, we'll do maybe some implicit differentiation on both sides. So we have 2y times dy dx equals, and here I'm just going to quote the quotient rule. So I'll just write it out first. So taking the derivative of x minus 1 over x squared. So this is going to be v times du. So x squared times 1 minus u times dv, so x minus 1 times 2x,
Yep.
all over x squared squared, which would be x to the 4. And so if I maybe just clean this up a bit, this is going to be x squared minus 2x squared plus 2x over x to the 4, which would be 2x minus x squared over x to the 4. And since x is bigger than or equal to 1, I can cancel out an x with no worry. So this will be 2 minus x over x cubed.
Yes.
So that there would be the value of 2y dy dx. And so therefore dy dx is 2 minus x over y x cubed. And y was x minus 1 over x squared.
Is it
So
not
this is 2
2y?
minus... Oh, sorry, yes, sorry, yeah, thank you, yeah. So it should be 2y there. So 2 minus x and 2y. So y was x minus 1 over x squared. So 2 times x minus 1 over x squared times x cubed. So
Square
there'll be a little
rooted,
bit of
no?
cancellation. Oh, sorry.
Square rooted, y squared is equal to
Oh
x
yes,
minus
sorry,
1 over
sorry.
x
Yes,
squared.
yes, yes. You're absolutely right. Sorry, I'm being a bit too rapid on this. So the square root, but again, as I mentioned before, I can focus on the positive square root and just focus on what happens above the x-axis. So for the time being, I'm just going to take the positive root, which will be root x minus 1 over x. Um, yes, over x multiplied by x cubed. So 2 minus x over 2x squared root x minus 1. So hopefully I've done that correctly. There may be a small algebraic error there.
No, no, it's fine.
Okay, awesome. Perfect. So the purpose of finding the derivative here was mainly to find the coordinate of the turning point. Maybe this will prove useful for some other means, so I'll bear that in mind. But for the turning point, we simply need to make this equal to 0, and that just corresponds to making the numerator 0, and that will be when x is 2, very clearly. So I know there's going to be a turning point roughly here, if I keep it to scale, or maybe slightly more inwards, when x is 2. And I should ask myself, okay, well, what's the y value? Because there's two possibilities here. Either it has a turning point somewhere here, but beneath the ln x curve and then
Yep,
decreases, or it kind of comes up like this, and then there'll be some extra points of intersection.
yep.
So I should ask myself, what's the y value on this green curve? I'm just going to get rid of this little part there. When x is 2, so I'll pop this underneath. When x is 2, y squared equals 2 minus 1 over 2 squared, which is 1 over 4. And so that means that y is plus or minus a half. But again, I'm just going to focus on the upper half for now. So I know that the y value here will be a half. Now the question is, well, what's the ln value here? So that's ln of 2. And just from my experience, I know that ln of 2 is roughly speaking 0.7, I think, to one decimal place. And so a half will be slightly less than that. So a half is maybe just under here. So the graph is going to have a turning point there. And I guess one thing you may ask is, well, do I know that this is a maximum or a minimum or a point of inflection? And I kind of already know that it's got to be a maximum because from what I did when I took the derivative, if we firstly the function is nice and continuous for x bigger than 1, and so I don't have to worry about any asymptotes or any kind of the graph jumping anywhere. And clearly there's only one turning point because there's only one value of x which makes it zero. And we know it has to be a maximum because it kind of has to go from being at a small value to another small value. And so it must turn around at a maximum. And so I believe the graph will, broadly speaking, look something like that. And then, of course, because of symmetry, maybe something like that underneath as well. So they get rid of those parts. So that's what the graph will look like. And so therefore, the number of points of intersection is simply one when x equals one.
Is there any other way this graph could look like, especially around the neighborhood of x is equal to 1?
It could also be concave. Sorry, yes,
Yes.
concave.
Okay. Yes.
So it could look like this. Okay, that's not, yes, that's something I should have considered. Um, so how do I establish if that is the case? Um, well, I think probably the best thing to do is just consider the value of the gradient of the curve when x is 1. So
Yep.
I know that ln of x, well, we can work out the gradient in a second, but we can work out the gradient of the red curve at 1 and work out the gradient of the green curve at 1. And that's
Yep.
going to tell us which one's going to grow more quickly. So, I mean, the graph could still be maybe convex, but also underneath the thing. So it's not actually of interest to us whether it's convex or concave. It's simply which one has a steeper gradient. So I should
Just
consider what.
quickly, how
Oh,
could you
yes.
take your formula for the derivative of the function and think about the
Mhm.
limit as x tends to 1? What is that derivative tending to?
As x tends to 1, how would I? Okay, so I see the issue here is that the denominator has a 1 minus 1. If we kind of put x equals 1 in, that'll be division by 0. But what I do notice is that the numerator is completely fine when x is 1. And so that tells us that this limit is either going to be positive infinity or negative infinity, broadly speaking. Um, so what I could do here, there's various ways I could approach this, but I think the simplest way would just ask myself, well, is it a positive gradient or a negative gradient? And we know it's got to be well, well, positive gradient is going up. But you could just plug in, for example, x is 1.01 and think about what happens. So the numerator here will be positive when x is 1.01. This thing here will be positive, and this thing here will also be positive, but it'll be just a slightly positive, it'll be like 0.01 or something. And so everything here will be positive, but because we're dividing by 0.01, it's going to be, 100 or something, a very big positive number. So we know that this is going to be very, very steep, whereas the lnx graph has gradient 1 over x. When x is 1, that's just 1. So it's a fixed like constant of 1. So we know that the green graph actually does something like this. If I maybe get rid of that part, so it's going to actually look something like this. Oh, actually, no, that suggests there's a turning point there, which I know there isn't. So, oh, sorry. Um, it's probably going to look something like that,
Yep.
where there's
Nice.
two intersections there and at one, and then yeah, just for completeness, the symmetric part there. Um, so yeah, I believe it will have 2 points.
Yes.
Um,
Very nice. And we can also approximate that to be very close to a half, but just less than a half. Cool. Let us move on to some probability now. Thank you for your work
Sounds
on
good.
calculus and logarithms. So, this is a probability question. So, suppose you're given a quadratic, which is y is x squared plus alpha x plus beta. Alpha and beta are uniformly distributed between 0 and 1, which basically means they can take any value with equal probability between 0 and 1, any real number. If I were to ask you, what is the probability of our quadratic y having 0 real roots? So intuitively, if I were to simulate this in Python and generate, let's say, 100 million combinations of alpha and beta, and I sketch all those corresponding quadratics, what is the probability of them not having any real roots so they don't intersect the x-axis? How would you think about this?
Okay, nice. So lots of thoughts are coming to my head, both from an algebraic point of view, but also from a probability point of view. So maybe the first thing that comes to my mind when I'm thinking from a probability viewpoint is, are alpha and beta independent? Am I assuming they're independent?
Yes.
Okay, so alpha and beta are independent. And the second thing is, this is a nice quadratic. This will always be a quadratic. It's not as if there's like an alpha term here and I'd have to worry about what happens when alpha is zero. This is always going to be a quadratic, and therefore I can simply determine the number of real roots because all the coefficients are real. The number of real roots is purely going to be determined by the discriminant. So
Okay.
this is equivalent to saying what's the probability that the discriminant of this quadratic is negative. The discriminant is going to be alpha squared minus 4 times 1 times beta.
Just quickly, before we move on, can you tell me what is the derivation of the discriminants? Where is it coming from? And why would you impose the condition of the discriminant being negative with the quadratic having zero real roots?
Okay, so if we take an arbitrary quadratic, let's just
Yep.
say ax squared plus bx plus c, where a, b, and c are some real numbers, and in particular a is non-zero,
Yep.
then we can from this, if this is equal to zero, sorry, we can, which is what we would assume if we're searching for root x of this equation,
Yep.
we can apply the quadratic formula, which essentially the quadratic formula is not just a magic formula, it comes out via completing the square on this
Yes.
equation.
Very
But
good.
it turns out that then x is minus b plus or minus the square root of b squared minus 4ac over 2a. And this thing here, the b squared minus 4ac, is what I refer to when I talk about the discriminant.
Very good.
And so, oh, sorry.
Yeah, very good.
Oh, yeah. If if we're talking about y having no real roots, we're essentially saying that this thing here is not a real number. And now the issue is if b squared minus 4ac is some positive or some non-negative number, either zero or I don't know, nine or something, or whatever, a non-negative number, the square root of it is very well defined. There's no issue there. It will be some real number. Minus b is a real number, 2a is a real non-zero number, and so x would be a real number. And so there would be real roots. The only possible way of this not being real, any kind of hope of this not being real, is if b squared minus 4ac is negative, and therefore you're taking the square root of a negative number.
Yes.
Um, awesome. So shall I return back to this problem over here?
Yes, please.
Okay, so we've boiled the problem down to saying what's the probability that alpha squared minus 4 beta is negative, or in other words, what's the probability that alpha squared is less than 4 beta? Um, okay, so we can work this out exactly, and I'm confident that I know the computation behind this. But before I just dive into computing some integrals or computing some values here, I want to think firstly, is there a simple, like nice symmetric way of solving this? And secondly, are there any maybe things that I can just observations, maybe to try and approximate this value? I do notice that if beta is bigger than 0.25, 4 beta here will be bigger than 1, and the probability alpha squared is less than 1 or less than 4 beta then, if provided beta is bigger than 0.25, that's guaranteed to be 1. And you may ask, okay, so then what's the probability beta is bigger than 0.25? Well, there's at least, well, that's 3/4 chance. So I know that this number here should be bigger than 3/4 because like guaranteed we get for free if beta is bigger than a quarter, this alpha squared will be less than 4 beta. But even if beta is less than a quarter, there's still a chance that alpha squared can be less than 4 beta. Um, so it's going to be bigger than 3/4, so a pretty high probability. But of course, maybe we want the exact value. So the way I'm going to do this is kind of condition this on two things, whether beta is bigger than a quarter or not. So I'm going to be using the law of conditional probability. So this
Before
is
you
the
do that,
probability. Oh, sorry, yeah.
before you do that, is there any alternative method you can think of relating to graphs? And we'll come back to this at the end.
Okay. An alternative method using graphs. potentially. So I'm not sure if this would work, but when you mention graphs, the thing I'm maybe thinking of is I know what I can maybe sketch the probability distributions of alpha squared and for beta and look at maybe when one of them is less than the other, and maybe have to compute an integral or
Or maybe think about if I were to sketch an axis with beta on the y and alpha on the x, and I know that their values are sort of like in this square and uniformly distributed, which means any coordinate in this square corresponds to one combination of alpha and beta. Can I use this sort of approach?
oh, I see. Yes. So okay, yeah. So if I first maybe draw the line beta equals alpha squared over 4,
Okay.
so that's a quadratic, so that's gonna and well, so it's gonna when alpha is 0, it's gonna pass through there. When alpha is 1, it's gonna pass through here. So it's a kind of a parabola of maybe looking like this, and it would carry on out here and sort of thing. And I want so this here is a quarter. I want I want beta to be bigger than alpha squared over 4. So I'm talking about points in this region.
Okay.
So I simply need to calculate the area of that in proportion to the area of the square, but conveniently the area of the square is just one. So in other words, I just need to calculate this shaded red area. Um, and that's probably the easiest way to do this is just do 1 minus this green area down here.
Okay.
Um, which I believe would give us the answer. So I can calculate that integral, but I just want to verify, or just want to think if that is actually the right approach. So I think that I guess here the crucial fact is that alpha and beta are nice. They're very nice random variables, and that they have the same distribution and they are uniform. I'm not sure if this would work in general with other distributions, but um, yeah, I think this would work because essentially yes, I guess another way to think about this, maybe sort of what you mentioned, but essentially we are in choosing alpha and beta uniformly from 0 to 1 independently. Essentially we're choosing a point randomly from this square, and so it's essentially what's the probability it's in this red area. So yeah, that's just going to be 1 minus the integral from 0 to 1 of this curve here, which is x squared over 4 dx. Um, yeah, and so then that's going to be 1 minus so x cubed over 12 from 1 to 0. So 1 minus 1 over 12, which is 11 over 12, if I've done that correctly. And that, I
Yes.
guess, just from looking at this, looks about right. That the red area kind of dominates this. Um, so the answer would be 11 over 12.
Very nice. Now think about integrating with respect to the y-axis and deriving the same area. How would you go about doing that?
Okay. So just to clarify, so we still have this same setup as here. You want to work out the red area now by still the red area, right? But all
Yes.
by thinking
Yes.
about integrating on the y-axis. Okay. So
Yes.
if I maybe just erase my shadings here. Um, so we can, I think the easiest way to do this from the y-axis point of view is to kind of split this up into two areas.
Yep.
So, so rectangle here, I'll maybe call this rectangle 1, and then this area here, which I'm going to call 2. So 1 is nice and straightforward. That's a rectangle. The height here is 3/4. The width here is 1. So that's going to be pretty straightforward. The area of 1 is 1 times 3/4, which is 3/4.
Very nice.
Two is the two is the more interesting one, I guess. So we're doing an integral. What are the limits of the integrals? Well, it's firstly going to be y limit. So it's going to be the integral from y is 0 to y is a quarter of something dy. And I want to think about what this graph actually is. So we know if I just swap this to x and y, so alpha is x and beta is y. Here is the graph of y equals 1/4 x. Yes, 1/4 x squared. And so if I fiddle about with this, I get 4y equals x squared. And so x is the square root of 4y because we're only looking on the positive side of x. So we don't need to worry about like plus or minus. It's just the positive one. And so this is going to be 2 root y. So this function here is just 2 root y from if we kind of rotate our heads sort of thing. So um, what we'd be integrating from 0 to 1/4 is just 2 root y dy.
Yep.
Oh, sorry, I missed that. Did you say something? Sorry.
No, that's good.
Okay. And yeah, and then we can just compute this. So this is 2y to the half dy. Add 1 to the power, divide by the new power. That's going to be 4/3 y to the 3/2 from 1/4 to 0. When I plug in 0, it vanishes, so I just need to focus on 1/4. So it's a 4/3, 1/4 to the 3/2, which I believe is going to be an 8. So 4/3 times 1/8, which would be 1/6. So that's the area of 2. And so therefore the total area, this probability that alpha squared is less than 4 beta, is equal to 3/4 plus 1/6, which is going to be 9/12 plus 2/12, which is the same as before, 11/12.
Very nice. Okay, thank you, Jamie. That was the correct answer. That ends the end of the mock interview. Thank you for taking part. Let me give you some feedback on your
Thank you.
performance. So we'll go question by question. I think your differentiation skills were very good. You were very concise and speedy. Just make sure maybe you can give extra detail, like derivations, even if it is only verbal. You can just say one sentence like the left-hand side is derived from the chain rule.
Thank you.
The graph, again, you were very good with the limits and intuition, and you realize that it's going to be above one, the asymptote, and it was nice in terms of using what you learned about the derivative as well. The next question was a bit more, had a few more sloppiness. I think you can go a little bit slower to make sure you don't make silly mistakes. Secondly, for the graphs, after I gave you the hints that it could look something like out, it could look like something else, you were pretty quick to realize what it could look like and tried proving it with the correct method. I think that was good. Also, by framing your answer by first giving observations, made your future life easier because then you realize that when the curve is below the axis for x greater than 1, there's no intersections. So that was really good. I appreciated your commentary throughout. The next part of the question was again pretty nice. You were very quick with the integration, as well as integration with respect to the y-axis. You also showed me the areas graphically. That was something good, so I could see your understanding. So there was no issues with that. And you also proved that it is the same area in both situations, therefore providing rigor and like verifying the answer. So that was really good. Overall, I think the interview went really well. Given this performance, you'll probably get an offer. So well done.
Thank you.
Um, I think for future, maybe just being a little bit slower to make sure there's no silly mistakes. But overall, it was good. You also followed my hints really well. That showed you were really teachable. That is something in particular that Oxbridge tutors look for. And the commentary that you provided for your answers before and while doing it was also something I really appreciated. So that was really good. What do you think of your performance? How do you think that you did?
Yeah, so firstly, thank you for the questions. I enjoyed them and definitely got me thinking. I was maybe I didn't really prepare too much, and I maybe showed it sometimes. And it's also been a while since I've done some of these sorts of this type of math, but found the problem really interesting. And so if you maybe look for the first problem, in a way, when we you told me we were going to do a mock interview together, I kind of knew graph sketching was likely to come up. It comes up quite often, and you can never really predict which types of graphs to sketch. But I think from doing lots of these problems before, I know that the general things you want to think of are maybe intercepts, asymptotic behavior, what happens as x approaches the kind of endpoint. So in this case, it was as x approaches one, I think it was, and x approaches infinity. thinking about that, and also then thinking about turning points, and there may be other things like other vertical asymptotes. Is the graph continuous? Is it odd or even? But I built up a repertoire. So I think that the first part went okay. In terms of you asked me to find the derivative. I agree that I could have explained some things, some more. I think yeah, it's a tricky thing to know kind of how to what extent you must explain things. At what point do things become trivial? But I do agree that if it's just adding another sentence, it's very easy to do um, whilst talking. Um, then the calculation, the sketching this graph of ln x to the 1 over x. Yeah, I think I made a couple of small mistakes, or maybe it was just kind of I was speaking the maths but not doing the maths. Where I think I said like the graph should approach zero, but then you corrected me, it was one. Which I don't think would be personally a major thing in an interview, but a major deal. But it would have been nice to have recognized that it was one. Um, yeah, but then I agree that the second part of that question, I made lots of silly mistakes from kind of just diving through it more quickly, and I think that was out of maybe eagerness to kind of to get through the non-trivial maths. But I guess it does highlight that it is important to make sure you're getting the trivial calculations correct. Obviously, it's not a trivial derivative, but it is like not the most exciting part of the interview. They expect you to be quite comfortable with taking derivatives and things, and so it is useful or is important to be careful. So maybe that's if I was actually sitting in the interview in a few months' time, that's maybe something I would practice is taking derivatives, also explaining how to take the derivatives and trying to do that quite quickly, but also accurately and not making as many mistakes. Um, so yeah, I think that was nice for the first problem. For the first problem, I think the hints were very useful. I should have considered whether it was, what the behavior was. And that's something I think in terms of graph sketching is another useful thing to consider for candidates preparing is if you're looking at two graphs on top of one another, where they intersect, it's thinking about which graph wins the race after that point. So which one goes higher or lower just after that point. So
There's
that's something I should have
also,
considered, but I think with the hint, yeah.
yeah, there's also like TMUA questions similar to this where you have to consider like the derivative to work out if like one graph is over or under to work out the number of intercepts.
Yeah, absolutely. Yeah, it's yeah, definitely I've done these types of things before. I think maybe the time pressure and the interview would have maybe hindered my performance slightly. But yeah, absolutely it's important to consider those things. Um yeah, and I think maybe it's a useful observation that some of the observations like the fact that it's symmetric about the x-axis is quite useful. In this case, I guess not really because underneath the x-axis, there's not going to be any points of intersection, but there very well could be in other instances. But purely in terms of sketching the green graph here, the x minus one over x squared graph, it might be useful to make that observation. So I know that okay, I can just focus on the top half, and then once I've drawn that, I just reflect it in the in the x-axis. Sorry. Um, but yeah, a bit sloppy on my part from with some of the calculations, but I think in terms of most of it with the hints as well. And I guess it should also be pointed out, I can't remember if you mentioned this or not, but hints, like it's not a bad thing if you have to take a hint. Everyone makes mistakes in the interview or overlook something. So as a student, someone who's sitting the interview, if they give you a hint, don't think of it as, oh, you've messed up majorly. It's more just maybe you've in my case, they just completely overlooked something and they're just trying to probe you to go, actually, have you just considered this? So you mentioned like that kind of phrasing a couple of times, and then realized, oh, I've forgotten to consider this or something. Um, yeah. So I think yeah, the first one did okay on. Maybe could have been slightly less sloppy as you mentioned, but I'm not I'm not too disappointed. Um, yeah, the second one, in terms of the problem, I thought was quite an interesting one, and I'd forgotten this technique. I've definitely seen this technique before of sketching this square and calculating areas, but um, I just must have slipped my memory. But well, initially, when computing this, I was thinking of, as I mentioned, kind of doing this by conditional probability. And you asked how I knew about the discriminant being negative. That's something I think every student should know, because it's actually surprising how many students don't know why the discriminant being negative has an impact. Well, why is it that has a correspondence with the number of real roots of a quadratic. Um, and I guess should, whilst I'm here, it should be mentioned that it is important that A and B are real numbers. If A and B are allowed to be complex, then the discriminant being negative doesn't necessarily mean you have zero real roots, because potentially there's some cancellation here, or if B and A are complex numbers. Um, but yeah, if all of A, B, and C are real, then the discriminant is going to dictate how many roots you have. Um, Anyway, yeah, I think once you gave me this hint, I think I was, as you say, it was okay in terms of I realized, okay, it's something just to do with area. An area can be computed via integrals. And then yeah, you said to integrate by the y-axis, and I've seen things like this before. It's just kind of you rotate your head 90 degrees and go, okay, instead of looking at like horizontal strips like this, you're now looking at sorry, vertical strips like this, you're looking now at horizontal strips like this, and calculating area that way, which is a nice little technique. And there's lots of interesting theorems that I remember studying at university in maths, which you can show that two things are equal by considering areas horizontally and then areas vertically, and you get some really interesting results.
Isn't like the vertical strips the Riemann integral, but the horizontal one is like the Leibniz one? Like a different type?
So like a Lebesgue, or like
Yes.
the Lebesgue integral, sort of, yeah. So, something along those lines. It's been a while since I've done it, so I'm not sure if I'm in the best position to explain, but it is something along those lines. And certainly from a pure math point of view, Lebesgue integrals are just a bit more general. It can be proved that, for example, Lebesgue integrals exist whenever Riemann integrals do, but the other way around is not true. Something like that. It's been a while since I've studied these. Um, but yeah, for nice and continuous functions, both of them are quite useful. But you can get some very nice identities by considering, um, yeah, both ways.
Cool. We can end the
What would your best if I was an actual student preparing for an Oxbridge interview in maybe like a month's time or so, what would your best piece of advice be to me based purely off of this interview here?
um I think in terms of verbalizing your thoughts, you're in a really good place. Math was very quick and mostly accurate. Um, I think my biggest tip would probably be, I'm not sure, you did pretty well. Um, Maybe because your foundations were strong, maybe you could look at more advanced material. So maybe you can try and push yourself by looking at harder questions now. If you're solid on the foundations, that could be a nice tip.
Okay, yeah. Yeah, I agree. I mean, obviously, you can only assess so much in a quick interview like this. We looked at a probability question and a calculus question. For a maths interview, there could be many other things like graph theory that could come up. It could be maybe some sort of trigonometry, or like some sort of using sines and cosines. It could just be a completely different problem, geometry, or a problem which you can't even really construct or like even prepare for really. So it's difficult to assess in just a short amount of time. But yeah, I think I kind of agree that if I was preparing, I'd look like I've got a good foundation, but I don't want to get too complacent. I want to really expose myself to more interesting, more difficult maths, more or just a broader selection of maths as well. But yeah, one of the things that I think was the main thing here was just being a little bit like sloppy and kind of rushing too much. But I think that might just be out of me being a bit out of tune with doing these calculations. So most of these derivatives and stuff you practice a lot in detail at A level, sort of just before you come to university. But then at university, you don't certainly in a maths course, you wouldn't actually do too much differentiation, and so on. Maybe in first year, and maybe in an applied course, but pure maths less so.
In economics, we do a lot of differentiation throughout all 3 years.
Yeah, I can imagine. I can imagine. Yeah, because I guess economics is like a version of applied math, so can completely understand that.
Okay, thank you so much.